Hello, welcome to a multi-stage description of roughness effects in turbulent pipe flow. This work, by extending a recently proposed theory for smooth pipe, gives an accurate description of friction factor and mean velocity profile in turbulent rough pipes. Take a look at experimental data of friction factor in pipes roughened with different sound grains. The colored symbols are measured by Nicholas nearly 80 years ago, and the dark stars are from Princeton superpipe. The question is, what's the difference between rough pipe and smooth pipe? Can we give a full description for all of this data? To study this, Goldenfield proposed a data collapse by the intriguing analogy between turbulence in rough pipe and critical phenomena. In 2009, Tao generates another collapse by postulating a composite scaling variable. However, both of them failed to collapse Princeton data due to incorrect power law scaling of friction factor at a high real number. We collapse all of the data by introducing the mean flux defect in rough pipe compared to smooth pipe. The mean flux defect is also called Hammers function, which is a universal function of normalized roughness size. Furthermore, we give an explicit expression of the Hammers function by defining a scaling function per se. The experimental data shows three power law scaling states with sound physical explanations. The first is hydronically smooth regime, where the roughness is buried within the viscous sublayer, thus the roughness effect is negligible. The second is transitional rough regime. In this regime, as the viscous scale gets smaller, the roughness encroaches upon the buff layer. Roughness-induced vehicles interfere with near-wall structures, modifying the viscous generation cycle and shaping new scaling of mean flow. The last is fully rough regime. The roughness-induced motions take over, totally destroying the near-wall viscous cycle. The mean flow is dominated by roughness, independent of viscosity. The existence of the local scaling is a prerequisite for defining dilation group invariant states for roughness-induced turbulent motions, implying that the transition between different scaling states satisfies generalized Lie group invariance property that we have discovered previously. We thus have the complete multi-state formula for the scaling function per se. Using per se, we can write down an analytical expression of friction factor in rough pipe with sound grains, in good agreement with experimental data. Another prediction in our theory is the mean velocity profile in rough pipe. According to Nicholas, per se is the effective roughness, but in our work, it defines the effective pipe radius and Reynolds number. We can transfer the mean velocity profiles from smooth pipe to rough pipe, and the accuracy is pretty good, bounded within 1%. At last, the only one free parameter p in the function per se uniformly characterizes different distribution of roughness size. For example, chimerical pipe, wrought iron pipe, and tar-coated iron pipes. It offers a potential choice to substitute widely used multi-chart in engineering.